Good day everyone. Welcome to my channel, where physics learning is highly possible and important to the author. Aside from finding micro solutions for problems of poverty through urban gardening, he is also trying to make learning physics easier for everyone, despite of the present condition where face-to-face classes are not allowed and teaching and learning could be safely possible through online or virtual classes only. Today in this session, a virtual experiment about the Newton's second law of motion will be performed. The author hopes that you will attain the objective of this experiment. The objective of this virtual experiment is to study Newton's second law of motion and its applications. To attain this objective, the following materials will be used: the iron stand, smooth running pulley, meter stick, stopwatch, thread, hanger, and weights. Important information significant to this video lesson. The laws of mechanics are embodied in the general principles of the laws of motion, formulated by Sir Isaac Newton. Newton's second law of motion states that when there is a net force acting on a body, the body would accelerate in the same direction as the net force. The acceleration produced has a magnitude that is directly proportional to the net force and inversely proportional to the mass of the body. In equation, acceleration A equals net force, F sub net divided by the mass m, or the acceleration is equal to the ratio of the net force and mass. Consider two identical masses connected by a light flexible cord passing over a light frictionless pulley. Since the masses are equal, the system is in equilibrium. That is, it will remain at rest, or if given a slight push, it will move with uniform speed. If a small body is added to one of the masses, the system will move with an acceleration A that is proportional to the magnitude of the additional force. The procedure: fix a smooth running pulley about 1 meter from the floor using the iron stem. Pass a piece of string over the pulley and at each end tie snugly a 30-gram mass. Add an extra 10 grams to the left mass so that the actual moving net force is due to the weight of the additional 10 grams. Hold the mass to prevent its descent. Find the time t in seconds for the heavier mass to descend from the starting point to the floor. Start the stopwatch simultaneously with the release of the heavier mass. Be sure that the time recorded is only up to the time that the mass touches the floor, not after it has fallen to the floor. Measure the distance S through which the heavier mass had descended and calculate the acceleration from the formula. Distance S is equal to 1/2 of the acceleration times the square of time, or the acceleration is equal to 2 times the distance S divided by the square of time. This is the first equation in finding the acceleration in this experiment. Consider the greater mass going down as m sub 1 and the smaller mass going up as m sub 2 and compute the acceleration from the formula. Acceleration A is equal to m sub 1 minus m sub 2 divided by the sum of the masses m sub 1 and m sub 2 times the acceleration due to gravity, g. The value of G is 980 centimeter per second square. This is the second equation for determining the value of acceleration in this experiment. Repeat procedure 2 by using a 20-gram mass to provide the actual moving force, and repeat steps 3 to 5. For the third trial, combine the two loads used in steps 2 and 6 as the actual moving force and repeat steps 3 to 5. Enter all data and results in the table. A more specific instructions about the combination of masses will be given as we proceed to the experiment. The next slide is the video on how the experiment is performed. Watch and learn how the materials are assembled and observe how the weights are combined to obtain the different net forces. As the heavier mass is increased, how is the difference in net force vary? How about the time of fall? How does it change as the difference in the masses or the net force increase? How can the error in this experiment be reduced? Silently watch this video. Data collection for this experiment starts in the next slides. In collecting and recording information, you need the activity sheets, a pen or pencil, paper, and calculator. While collecting data and recording measures, you may need more time, more than the playing time of this video. In those instances, you may pause the video. This table is the same as the table in the activity sheets. Record your measures and observations here. Note that there will be sub-trials for every trial to lessen the error in taking the time using the stopwatch. Let's start the behavior of the system of masses when the masses are equal. The masses of the hanger and weights are obtained using a digital balance. The masses m sub 1 and m sub 2 are equal and both 27.6 grams. In this experiment, only m sub 1 will be changed. When m sub 1 and m sub 2 of the same masses were hung at the ends of the thread passing through the smooth running pulley, none of the masses descend or move downward. Why? What could have caused this equilibrium? That is because the sum of the forces acting on its mass are equal. Now let's start. For the first trial, the masses will be determined, particularly m sub 1. Read and record the mass of m sub 1, while m sub 2 remains the same. The system of masses, where m sub 1 is greater than m sub 2. Measure and record the height of fall, S, and the time of fall. For sub-trial 1, the time of fall will be obtained using the stopwatch. Hold the behavior mass to avoid descending ahead of time. Ready? Start at the release of m sub 1 and stop once m sub 1 touches the floor. Observe the duration of fall. Read the time recorded in the stopwatch and record properly. For the next sub-trial, for trial 1, position m sub 1 and m sub 2. Measure the height of fall. It's the same as the first sub-trial. Measure the time of fall using the stopwatch. Observe carefully the release of the behavior mass. Start the stopwatch and stop once m sub 1 hits the floor. Read and record the time of fall for sub-trial 2. For sub-trial 3, for trial 1, position m sub 1 and m sub 2. Measure the height of fall. It's the same as the first sub-trial. Measure the time of fall using the stopwatch. Observe carefully the release of the heavier mass. Start the stopwatch and stop once M sub 1 hits the floor. Record the time of fall for sub-trial 3. Now for trial 2. Measure the mass of the hanger with weight and record as M sub 1, while M sub 2 remains the same. The system of masses for the second trial, sub-trial 1. Measure the distance of fall as record on the table. The distance of fall is kept constant or the same with the first trial. The time of fall will be obtained using a stopwatch. Hold the heavier mass to avoid early descent. Taking of time and release of M sub 1 should be synchronous. When done, read the time of fall and record on the table. For sub-trial 3, for trial 2, position M sub 1 and M sub 2. Measure the height of fall. It's the same as the other sub-trials. Measure the time of fall using the stopwatch. Observe carefully the release of the heavier mass. Start the stopwatch and stop once M sub 1 hits the floor. Read and record the time of fall for sub-trial 3. For sub-trial 3, for trial 2, position M sub 1 and M sub 2. Measure the height of fall. It's the same as the other sub-trials. Measure the time of fall using the stopwatch. Observe carefully the release of the heavier mass. Start the stopwatch and stop once M sub 1 hits the floor. Read and record the time of fall for sub-trial 3. Now for trial 3. Measure the mass of the hanger with weight and record as M sub 1, while M sub 2 remains the same. M sub 1 is now greater than M sub 1 for trials 1 and 2, which means the difference in the masses increases, and the net force is also increased. The system of masses for the third trial, sub-trial 1. Measure the distance of fall as record on the table. The distance of fall is kept constant or the same with the other trials. The time of fall will be obtained using a stopwatch. Hold the heavier mass to avoid early descent. Taking of time and release of M sub 1 should be at the same time. When done, read the time of fall and record on the table. For sub-trial 2 of trial 3, hang the M-1 and M-2 properly. With the same distance of fall as the other sub-trials, position the behavior mass above M-2. The time of fall will be recorded by the stopwatch. Make sure that the release of the behavior mass and starting the stopwatch are synchronized. When done, read the stopwatch and record the time on the table for sub-trial 2. Now for sub-trial 3 of trial 3, position M-1 and M-2. Measure the height of fall. It's the same as the other sub-trials. Measure the time of fall using the stopwatch. Observe carefully the release of the behavior mass. Start the stopwatch and stop once M-1 hits the floor. Read and record the time of fall for sub-trial 3. After measuring the time of fall in each trial, how do the values of the time of fall vary as the difference in the masses increase? For additional instructions in this activity, record the data, time for sub-trials, behavior mass, lighter mass, and height of fall on the table in the activity sheet provided. Compute the average time for each trial, the acceleration using equation 1, and the acceleration using equation 2, and percent difference. Show the computations. Answer data analysis, conclusions, and questions provided. Complete the report and submit to your instructor or professor. Before this video lesson or virtual experiment ends, the author recognizes the entire physics department. This virtual experiment was adapted from the laboratory manual developed by the faculty of the department. The video clips integrated in this presentation were cropped from the videos recorded by the following faculty: Professor Nelson Imabana, the head, Professor Danilo Violete, and Professor Richard L. Muhi. The author hopes that the objective of the experiment was met and the need to continue the teaching and learning process despite the unfavorable situation was satisfied. Your participation in the conduct of this virtual experiment was appreciated. Thank you for watching this video. Keep safe and good luck.